but we want to think about what are these M, H, and N's. And these M, H, and N's, we can think of it as a channel that has a state. And so let's just think about the potassium one first. So the potassium channel activation, this is an inactive state or open state, open and closed state, right? And we have some rate of moving from the closed state to the open state, and from the open state to the closed state, right? So alpha tells us the opening rate, beta tells us the closing rate. Okay? So how can we write this down? We can actually look at the change in the open states as a change in time is equal to, well, it's going to be the sodium opened, it's going to be alpha times the number of closed, which is going to be n open minus, 1 minus n open. We're going to talk about total probability. So 1 being the maximum. If all of them are open, there's nobody left to open up, right? And if all of them are open, then this is the rate at which they close, beta times the number of open guys, right? So we write a differential equation that describes the rate of opening and closing. It's dependent on what proportion of them are open and what proportion. These are also voltage dependent. We haven't gotten into the voltage dependence yet. Okay, so let's rearrange this equation just a little bit. If we rearrange it, we can rearrange it 1 over alpha plus beta times dn dt. We're only going to talk about open state, so I'm going to lose the. So essentially, I'm going to rearrange the n's here and then group the alphas and betas, and that's going to give us alpha over alpha plus beta minus n. So there's just one simple step in there I'm going to ignore. Okay, so if dn dt is equal to 0, that's the steady state solution. We're no longer changing the number of channels. And so if dn dt is equal to 0, this is what n is going to be equal to, right? So n equals alpha over alpha plus beta at t equals infinity. This is the steady state. And we're going to call this value n infinity. Right? That's the steady state solution. How quickly we converge to that steady state solution is going to be dependent on this value in front. Right? The bigger this value is, the faster dn dt, the larger dn dt is, the faster it's going to converge. Right? So this value here is going to tell us the rate. And that is we're going to call d tau n. So we have n infinity and tau n, which we can calculate directly from the alphas and betas, the rates of opening and closing. Right? So if we want to write a differential equation, often the easiest way is not to write it with the alphas and betas, but we often will write this dn dt is equal to, and then we can just write n infinity minus n over tau n. Right? So when n approaches infinity, dn dt goes to 0. Right? And tau n, the larger tau n is, the smaller dn dt is, the longer it's going to take to get there. Right? So this is the form that we're going to write. We're going to have a dn dt. Very similarly, we're going to have a dm dt, which is equal to m infinity minus m over tau m, and we're going to have a dh dt is equal to h infinity minus h over tau h. So when you put this dv dt, this dn dt, dm dt, dh dt together, that's the Hodgkin-Huxley equations. Those are the four ODEs that you use to record. N, M, H, and V are what we call states, right? How active are the sodium channels? How inactivated are the sodium channels? How active are the potassium channels? What's the current voltage state? Those are states. There are parameters in the equations, and parameters are things like, what's the maximum sodium? Yeah?
What is H? What ion is H for?
H tells you the inactivation of the sodium channel.
Oh.
Yeah, so it fits right here in this M times H.
Oh.
So there's parameters, and those parameters are the maximum sodium conductance, the maximum potassium conductance. There's parameters like what are the reversal potentials of these currents. There's parameters in the alphas and betas. And those are all the parameters of and those are just values that we put in. They don't change over time. They don't change in the simulation unless you explicitly put them in.